Okay, thank you very much to the organizers of the summer school for inviting me here to give a talk. I'm very happy. So, first of all, I'd like to start off by explaining to you basic sieve problems. So, Damaris talked a bit about sieves yesterday, but what I'm going to be doing is even more basic than what she was doing. So like real basic set of sieve problems are the following. So for each prime p, I'm going to let omega p be a subset of z modulo pz to the power of n. So let n be a natural number greater than or equal to 1. And for each prime p, we're given such a subset, and then the challenge, as it were, is to calculate or say something about the cardinality of the number of integer vectors x in z to the n, such that when I reduce this vector modulo p, it lies in my given set omega p. And this is for all primes p. So we're counting. I need a height condition, obviously. So and I'm counting, so in order to make sure it's a finite set, I need to stipulate the maximum of the absolute values of the coordinates is less than or equal to b. Here b is some real number which you're thinking of as tending to infinity. Okay, and in general, as this is stated, this problem is way too hard because, my p-adic, I'm imposing local conditions at each prime p, and these could be, at least as it's stated, completely arbitrary. But sieves are like a general machinery for helping you deal with problems of this type, where you've got infinitely many conditions imposed, one condition each prime, and you want to get, say, upper bounds for this cardinality, or maybe just show it's non-empty, for example. And today, we're talking about upper bounds. And here, one of my favorite ways of getting upper bounds is via the large sieve. So it states the following. So in the above setup, so I give this cardinality a name. So this is n omega of b. And here, capital omega is just the collection of all the omega p's for all prime p. And this gives you an upper bound in the following form. So it says n of omega b is less than b to the n over L of b to the half. So a few different versions. I'm chasing a version which I've optimized for the applications I'm going to explain in a bit, but there's kind of lots of different ways of stating it. But I'm choosing the simplest version I can state, which is required for the applications to come. And what is this cardinality on the bottom? So I'll define it for some parameter q. So you take the sum of all integers a between 1 and q, and you take those integers square free. So it's a Mobius function, and I'm squaring it. So this is equal to 1 if a is square free and 0 otherwise. So it's just a useful indicator function for square free numbers. And then you take the product over all primes dividing a of some quantity omega p. There we go here. So it's omega p, it's the proportion of excluded residues. So it's 1 minus the cardinality of capital omega of p divided by p to the n. So it's a proportion of residues which we're not counting. Okay, so what can I say about this further? So obviously, I'm counting integers in, n tuples of integers in a box of size b. So p to the n is like the trivial upper bound for this quantity, and the point of the large sieve is it potentially gives you some saving depending on this cardinality, depending on this quantity here. And I won't tell you how to prove this. I'm going to give some applications, but it's quite amusing. Yeah, it's proved using Fourier analysis on finite abelian groups. That's how it's proved. And there's lots of different versions of ways to state it, but the fundamental tool is Fourier analysis on finite abelian groups. So I'll tell you a nice application of the large sieve to thin sets. And I should say this application you can find in the book of Serre on lectures on the Mordauvet theorem. So you can find a statement of the large sieve in there, and he also proves, as you find a proof in there. So yeah, I find this book really funny because, I mean, the title is Lectures on the Mordauvet theorem, so probably you think it's all about just elliptic curves and proving the Mordauvet theorem. But that's like only one really small part of the book. The book's really huge, and it contains loads and loads of different topics, like to do with Hilbert's irreducibility theorem, large sieve, thin sets, heights, yeah, just like loads of useful stuff in there. Okay. So Emmanuel spoke about thin sets earlier today, but that was a couple of hours ago, and we've had lunch since then, so maybe I'll remind you. And yeah, my definition of thin sets is going to be slightly different to Emmanuel's because it makes it easier to use in practice, but the two definitions are equivalent, and that's an exercise to show the equivalent. Anyway, I'll give my definition now. So let X be a geometrically integral variety over field K. So yeah, so a thin subset, so this is definition of X of K is a subset of a finite union of sets, and I think I need to go back over here now. Hoping to, yeah, I'll move this up. So yeah, so it's a subset of a finite union of sets of the following types. There's two types of thin sets. Type 1 is the easy case. So it's just sets of the form Z of K inside X of K, where Z in X is a closed geometrically integral subvariety with, so it's a proper, yeah, not equal to it. So it's just sets of rational points on closed subvarieties. And type 2 is a more interesting case. So these are rational points which come from covers of X. So it's points to the form pi of Z of K inside X of K. Now, pi is a morphism for Z to X, where this is a generically finite morphism of degree at least 2 So by the degree, so generically finite just means if you look at the associated function fields, this is a finite extension of function fields, and I want this finite extension of function fields to have degree at least 2. So generally finite morphism of degree at least 2, and I'm going to assume that Z is geometrically integral as well. And maybe I should say, I'm not sure if it's already been discussed, but yeah, by geometrically integral, I just mean so that when I pass to a choice of algebraic closure, my variety is, so first of all, it's irreducible and it's reduced. But secondly, when I pass to an algebraic closure of the ground field, this variety is still irreducible and reduced. And it's not very necessary for the theory. You could basically reduce to this case, where you just consider geometrically integral things, and it makes just streamline some statements and proofs a little bit, but it's not integral to the theory. No? Okay. No. Cool. So I give you an example. So yeah, so say thin set is a subset. So you take in general to take a thin set, you take a union of sets of this type, and it's a subset of a finite union of such sets. So example, if I look at the sets of all points, well, yeah, elements of K such that X is a square. So I'm thinking this is a subset of the affine line over K. This is thin of type 2. And you see this just by taking what's our choice of morphism. It's just a map going from the affine line to itself, which sends X to X squared. OK, and you see already from this example that thin sets are really interesting over non-algebraically closed fields. Because, for example, if K is just an arbitrary field. So if K is algebraically closed, then obviously every element of K is a square. So in this case, yeah, the whole of this set of all rational points is thin. So it's only interesting theory when you're looking over non-algebraic closed fields. And somehow, the really interesting case is like so-called Hilbertian fields. So I won't talk about much about them, but for example, like number fields, example, the Hilbertian fields, this is where the theory of thin sets is most interesting. OK, so that's definitely now. I'll state the theory. So this film is due to Serre and Cohn, I guess. So Cohn proved it first. He basically gave a new proof in his book, which was a lot more streamlined. Well, Serre, yeah. He gave a look. This book using more techniques from algebraic geometry, made it a bit more conceptual, and improved the bound slightly. The one. You think it's OK, I don't have the precise reference with me. OK, thank you. So it's named the film. So let capital omega and Pn of Q be a thin subset. Then we want to count rational points of bounded height inside the set. So I'm giving definition of the counting function. Yeah, I'm going to be a bit cheeky and define the function and state the theorem at the same time. So all rational points which lie in omega whose height is less than or equal to b. And then the theorem states that this is bounded both by b to the n plus a half times b. OK. So for the heights, I should clarify. Yeah, so I mean, there's lots of different conventions. I mean, there's been many different conventions over this conference, over the summer school, about whether you're taking logarithmic heights or exponential heights. Normally, when you're counting rational points of bounded height, it's almost always better to use exponential heights. So and here for this height, it doesn't, since we're talking about upper bounds, it doesn't matter, because all choices of height at least over 1 are equivalent, but I'm choosing the normal naive height on projective space. So it's the maximum of the absolute values of the coordinates, provided I choose a representation such that the xi's integers whose greatest common divisor is equal to 1. So this is and so yeah, so number of rational points of bounded height in projective space. So you have m plus 1 coordinates, and this gives you naively b to the m plus 1 possible choices for rational points of bounded height, and this is correct. Apart from the GCD condition, you need to insert an extra factor coming from the Riemann zeta function to take care of it, but there's b to the m plus 1 rational points of bounded height in projective space. In particular, this says that most rational points in projective space do not lie in any given thin set, because this is much smaller than b to the m plus 1. And this factor log b can be improved slightly. This is what Serre did, but yeah, I won't go into that. Cool, and since this is an école d'été, I thought I'll prove this theorem because it's really nice proof. Yeah, using a large sieve. So say the proof is literally taken from this book of Serre on lectures of the Mordauvet theorem. Okay, so proof of the theorem 1. Right, we're going to use the large sieve, in case it's not surprising. So you see in the large sieve, we need to understand the proportions of the excluded residues. So we need to get a good idea of how many residues we're throwing away at each prime p. So this is what lemma does. Of course, lemma 1. So yeah, I'll state it for projective varieties, but it's not that important. You can have other versions for non-projective varieties, just making sure you work with integral points instead of rational points. But so that b, so x over q be projective, and geometrically integral. Yeah, smooth isn't important here. God, I can't read the bloody notes. Okay, then I'm going to let omega inside x of q be a thin set. And p a prime. And I'm going to write omega p for the reduction of omega modulo p. Okay, so here, again, I'm being a little bit naughty. In order to talk about reducing, yeah, if we'll talk about FP points, I need to choose a model, but any two choices of a model will differ by finite and many primes. And in everything I do in this whole lecture, I can always throw away finite and many primes. So I'm not too worried about such considerations. So I can talk about the FP points of x as long as p is sufficiently large. Actually, I guess since x is projective, you've even got a natural model. Yeah, so sorry. Yeah, so since x is projective, I've got a natural model just by taking the closure of x inside projective n space over z. So I can talk about reduction modulo p and what's an FP point. Okay, so that's the setup. Cool. So two cases. If omega has type 1, then I look at the number of points in my thin set modulo p, and it's less than p to the n minus 1. And here, I'm going to let n be the dimension of x. So this is the easy case. Interesting case is type 2. Then the following holds. So it says there exists a number field k, and a constant c, which is strictly between 0 and 1, such that for all primes p with 4 primes p which are completely split in K, we have the following bounds. So the point is we can't get good bounds for every prime P. There's only just some collection of primes of positive density where we can get good bounds. But what are the good bounds anyway? So for these special primes, we have the bound, so it's less than or equal to a constant times p to the n, and there's some error term. So it's p to the n minus a half. So yeah, so the thin set's type 2, the statement's a bit technical, but I'll explain the proof and give an example and try and illustrate where this number field comes from. Okay, proof. So yeah, type 1. So I recall what type 1 means. It lies inside the set of rational points of some closed subvariety. So in this case, you just need to observe the number of FP points on a closed proper subvariety is less than p to the n minus 1. And so it's actually really easy to prove this. There's a really nice proof, which I again learned from Serre, using thought normalization. Normalization. So I'll briefly explain how the argument goes when we write it. So yeah, in this kind of problem, we're allowed to replace Z by an open subset if we want to. And the no-thought normalization tells you that after replacing it by an open subset, it emits a finite cover to affine n, well, to some affine space. It's a finite cover of affine space. An affine space, you know how many points there are on affine space, and then it's a finite cover of affine space, so it's like, well, okay, so if Z was a divisor, then it'd be a cover of affine n minus 1 space, and affine n minus 1 space has p to the n minus 1 points, and it's a finite cover of the degree, so you just multiply it by the degree. So that's it. It's a very nice. Yeah. I don't know. Maybe it's clear to more people how no-for normalization is useful in algebraic geometry, but this is like my favorite application of it. Cool. That's type 1. It's type 2. So recall for you, it lies inside the image of the map for the rational points for some finite cover. I was hoping to keep this lemma, but I think it has to go. Yeah, so first, to try and explain the ideas, I'll first assume that pi is Galois and finite et al. So finite, yeah, so by Galois, I just mean the corresponding extension of function fields is a Galois extension of fields. In this case, it's really easy to prove the result. So I'm going to let x be a point in the image of the FP points. So Then I want to see how many points are in the fiber. Say the fiber over x. So this has exactly the d, where d is the degree of pi, fp points. And here, it's really important that my morphism is Galois, because what's going on, I've got the Galois group acting on the fibers of the morphism freely and transitively. So as soon as I have one rational point in a fiber, I move that rational point around, and it fills up the fiber with it. But the Galois group acts in the degree's fixed, so it acts kind of in the same way in each fiber. So as soon as I've got one rational point, I always get d rational points in the fiber. So this means we even have an exact equality. So the number of points in the image is exactly equal to 1 over d times the number of points on z. So yeah, it's really much easier to understand this case. OK, but now I assumed in my definition of type 2 thin set that z was geometrically integrable. And for geometrically integrable varieties, there's a really nice formula for the number of fp points coming from Langevin estimates. So Langevin estimates tell you, so this is, so it's p to the n plus big O of p to the n minus 1. I can't, in my definition of thin set, type 2 1, I can't remember if I emphasized in my definition of type 2 thin sets, but I think I might have forgotten to write it. Sorry. It's important that that the morphism pi is dominant. I'm not sure if I wrote that down. Anyway, the point is that z has the same dimension as x. OK, so here we have an explicit formula for it. And then this proves the result in this case, because we can prove the result with c is just 1 over d. And this result even held for all primes, or maybe all but fine many primes. So we didn't have this annoying thing about having to take a number field. So we could just take it with c is 1 over d and k is q. So how does this number field arise? This is relevant, and it's a non-Galois case. And I won't give a complete proof here. I'll just briefly explain what happens. So yeah, so if pi is not Galois, we take the Galois closure. So yeah, you've got theory. So I assume everyone's used to the Galois closure of a finite extension of fields. But Grothendieck also developed a theory of Galois closure of morphisms of schemes. So we take a Galois closure of this morphism of schemes, and it satisfies the properties you'd expect. And we apply a similar argument to the one I described in this situation, but what's different is that this set of Gao need no longer be geometrically irreducible. And you see in my argument here, it was very important that I was assuming Z was geometrically reducible to get this to work. So you take K to be the algebraic closure of Q inside the function field of the Galois closure. So this is the number field which is relevant to the statement of the lemma. And for primes which are completely split in this number field, all irreducible components of the Galois closure are actually defined over the ground field. And when you're in this case, you can apply a similar argument to what I've done to deduce the result. So, yeah. So the rest of the proof is exercise. Or maybe I'll give an example to illustrate this phenomenon, how this number field arises, because there's a really nice example. So example, so already said the set of squares in the field is a thin set. Let's take it to the next level. Let's look at cubes. So I'm going to look at the map. P1 goes to P1. I look over Q. And in affine coordinates, it's just x goes to x cubed. OK, then let's see what happens on the level of f points. So, well, OK, let's take the Galois closure first. So the Galois closure, on the level of function field, you just got q of x. And the Galois closure is taking a third root of x and then joining a third root of unity. So what does it mean on the level of schemes? This means you need to look at P1 over Q adjoin a third root of unity, mapping to P1 of Q. So this is the Galois closure as a map of schemes. And you see I'm here as a scheme over Q. So it's not geometrically irreducible. It's like got 3 copies, well, I guess 2 copies of P1, which are moved around by action in the Galois group. And how is this reflected in the proof? So you see that if P is congruent to 2 modulo 3, then we don't get any sieving on the size of this thin set because this map on cubes is bijective. So if P is 2 modulo 3, there's no third roots of unity in the field, and this means the kernel, as it were, where every fiber consists of 1 element, but these are finite, so and have the same cardinality, so it must be a bijection. So in this case, there's no saving at all. But if P is 1 modulo 3, which are exactly those primes which are completely split in this cyclotomic field, then we get a saving. Namely, the image is half of all elements lie inside the image. OK, now I can use the lemma to prove the theorem, which has since disappeared, but never mind, at least the large sieve is still there. OK. So proof of theorem 1. So if you recall, this is a statement that few rational points lie inside any given any thin subset of Pn. So reduce to the case of thin sets of type 1 and type 2 because it's just a finite union of them. And type 1 case, I'll just say it's easy. It follows. You can prove it. It follows a minor modification of the argument I'm going to present for the type 2 case. So we're in type 2 case, so it's the image of set of rational points with some finite cover, or generically finite cover of degree at least 2. Cool. Now we apply the large sieve, and that still exists. And our local conditions, so we're calling the sieve setup, we need some local conditions. Well, the local conditions, I just take my thin set and reduce it modulo p, as in the statement of the previous lemma. So you get up a bound of this form, b to the n plus 1. OK, so I stated the large sieve there for Zn, but here I'm working Pn, so the cover of affine space is affine n plus 1 space. So that's why I need an n plus 1 there. And I've got this aleph b to a half. So we just need to get lower bounds now for this quantity. So as we're interested in lower bounds, these omegas are positive, mu squared is positive. In order to get a lower bound, I restrict the range of summation, and rather than summing over all square free numbers, I'm going to sum over primes. And then we just have this omega p. Cool. But from lemma 1, from lemma 1, I got some upper bounds for this quantity. Well, I got upper bounds. So yes, this is a proportion of excluded residues, and lemma 1 is upper bounds for the number of included residues. So this gives us lower bound for the number of excluded residues. Put Q, hence P. The auxiliary number field K. And we've got 1 minus C, and there was, So omega p still exists. So the 1 is the 1 there, and I'm replacing this by minus C times p to the n over p to the n, but then the p to the n's cancel each other out. Cool, but there's a famous theorem due to Chebotarev. Whoops, excuse me. Chebotarev density theorem, which says you know how to count primes which are completely split in a given extension. Namely, well, I'll write it down as an asymptotic formula. So you 1 over c, it's the degree of the extension. And you have a prime version of the prime number theorem. So this is a normal term from the prime number theorem, but be factored by the density of the set of primes, which is 1 over the degree of the extension. And then recalling that we're taking to be b to the 1/2 implies that everything all together, here we've got b to the n plus 1, and we've got a b to the half log b over half, so altogether it's b to the n plus a half times log b, which was the statement of the theorem. Okay. So 20 minutes, nice. Any questions at all? Cool, now I'll move on to some homework, so I'll talk about generalizations of theorem 1. So, namely, yes, the general setup is, hopefully it's clear, you're given some variety and you're given some thin subset in there, and the question is, you count how many rational points lie in this thin subset, you know. Are there very few, could there be many, etc. And as Emmanuel explained in his talk, for some classes of varieties, you can get many rational points in a thin subset. So as an example, due to Batyarev and Chinkel, which he explained right at the end. So sometimes thin subsets can be accumulating. There could be lots of rational points in them. So we need to restrict to some class of varieties where we can hope to get very few rational points in a thin set. And, well, yeah, you need equidistribution, basically. So this general setup is as follows. So X be a Fano variety over Q. So yeah, more general, I mean, all the theorems work over number fields. I should work over Q for simplicity. And I'm going to so with a choice of adelic metric on the anti-canonical bundle, and I'm going to assume that there is a rational point, so that counting rational points is not trivial. Your Fano variety, I'm not sure if it's already been mentioned. Anyway, it means the anti-canonical bundle is ample, so that you can, if you count rational points of bounded height with respect to the anti-canonical bundle, there's only finitely many. So it's just a nice varieties to work with for counting rational points problems. Okay, and I will call for you definition from Emmanuel's talk concerning equidistribution of rational points. I'm not sure if he gave it in precise form, but anyway, I'll try to. So we say that the rational points on some open subset, well, open dense subset to U inside X are equidistributed if for all. So I'm going to look at, so basically you want, some measure to convergence in weak sense, but I can make this explicit if you don't like convergence of measures. So for all, so I take some subset W of the adelic points, which is open, whose, so he introduced a probability measure in his talk, so we want the measure of the bound. So it's not a pathological open subset. So for such open subsets we have, so I want to count the number of rational points which lie and U, whose height is bounded by B. So here I'm taking the anticanonical height given by my choice of adelic metric anticanonical bundle, and then we divide through by the total number of rational points of bounded height. So saying we have equidistribution means if we take the limit as b tends to infinity, this limit is equal to the quotients of the measures of the compounding sets. But as Emmanuel said, you need to be careful. You need to take the measure supported on the subset which is cut out by a Brown-Manny obstruction. And we normalize appropriately. So hopefully looks good. Okay. So this holds for, quite a few classes of varieties like flag varieties. So he mentioned in his talks, quotient of a, also toric varieties, this property holds. And in general, you need to remove some open subset to get rid of possibly accumulating subvarieties. Great. Now I can state Theorem 2, which is a generalization of the theorem of Serre I mentioned earlier, due to myself, Tim Browning. So, in the above setup, so I've got X my Fano variety. Okay, so if, so I'd say if X has the equidistribution property, on some open subset U, then, oops. Okay. Wait. Yeah, okay, then. Yeah, then for all thin sets, omega in x of q, we have so I'm going to take limit as b tends to infinity. So look at the number of rational points of bounded height in our given thin set. And then I divide through by the total number of rational points. Then the theorem says this limit is 0. So yes, in particular, yeah, most rational points do not lie in any thin subset. So notice, basically this is kind of like a little overresolve, if you like. In the theorem of Serre and Cohen, they got explicit upper bounds, which, given the generality we're working in, I don't think it's realistic to get explicit upper bounds, but we can still get a kind of, there's like a 0% result. And I wanted to say a bit about the proof. Yeah, it's not too long. It's quite similar. Yeah, once you know how to prove the Serre theorem, it's quite similar. So we could reduce the case of type 1 and type 2. Type 1, it's really easy. So assume omega has type 2. So assume omega has type 2. Okay, and we're going to want to use the equidistribution property. So we need to introduce some subset of the DAOs we're going to be using, and this it is. So I'm going to let m is just some number which I'm going to let tend to infinity soon. So for all primes less than or equal to m, I look at the set of p-adic points. Well, yeah. Okay, I'm not doing anything in the real place. It's not interesting in this case. So take set of all p-adic points. Reduction modulo p lies inside the reduction modulo p of our thin set, and at primes bigger than m, we do nothing. There's no p-adic condition imposed here. Okay, so the limit in the theorem. So rather than saying I want my rational point to lie in the thin set, I'm going to say I want it to lie in the thin set for all primes. But then if I want an upper bound for this, I can say I want it to lie in my thin set at all primes p, which are less than or equal to m. So the limit in question is less than or equal to the limit as b goes to infinity. So I just take the number of points which are in this set, a bounded height, divide through by the total number. See, I'm just imposing finite many conditions, and I'm going to let this capital M go to infinity at the end of the proof. Cool, but now I've got some p-adic condition imposed, and we assumed to begin with that we had equidistribution. So we know how to deal with this. So by assumption, it's asymptotic to the measure of W of m intersect the subset of the adelic points cut out by the Brown-Mannion divided by all of them. And if you recall, this omega x was a probability measure. So this fact on the bottom doesn't bother us. It's just some fixed number we don't care about. This guy on the top, however, if you want to calculate it, and maybe I can't. So I'll briefly explain how you deal with this Brouwer condition. So as Emmanuel said in his talk, the subset cut out by the Brouwer group, or maybe he didn't say explicitly, but for finite varieties, the Brouwer group modulo Brouwer group of Q is finite. And in this case, this is open and closed. And this has a product topology because X is projective. So it means this is like something weird going on at finding many places which you don't understand, but for all of the primes, it's just a product of all QP. Pardon? Oh, yeah, okay, yeah. Well, it depends how complicated your Brouwer group is. But anyway, if something goes wrong with finding many primes, but these finding many primes don't play a role here, so we don't care about them. And then all the rest of the primes, it's just like a product over all the QP points. So these don't affect any of this analysis. So we can ignore these. We could throw all these finding many primes into some unspecified leading constant that doesn't bother us. And then we just got the local measure of the sets I've defined over here. And then, since the probability measure is normalized by the total volume. But now, this volume, as long as you take a sufficiently large prime, this is just, well, making sure I'm taking quotients, well, right now. So these measures behave nicely with respect to reduction modulo P. In particular, I'm looking at the fiber, as it were, over reduction modulo P of omega P. So this is just the number of elements in omega P divided by the total number of FP points. Okay, but now lemma 1 comes to our rescue again. Because I was assuming, I was looking at a thin set of type 2, and lemma 1 gave us good bounds for this, at least for on a set of primes of positive density. So I'm going to let K and C be as in lemma 1, and now take the product over P, M, and P, which is completely split. In my number field K. And what was the bound? It looked like C times P to the power of N. And this cardinality on the bottom, you can apply the estimates. So you know this, because X is geometrically integrable here, this grows like P to the power of N. So lemma 1 plus Langevin. So lemma 1 deals with the numerator, and Langevin tells you this grows roughly like Ptn on the denominator. So these now cancel. Well, yeah, they cancel out. And now the implied constant here is independent of the initial parameter capital M. That's all my doing. And I know by Chebotarev there's such primes. So, and this number from lemma 1 is between 0 and 1. So I've got some number less than 1. I'm just multiplying it together infinitely many times. So now we're allowed to take M goes to infinity. And in this case, this above expression tends to 0. Because this bound is valid for all choices of capital M. So I just made my capital M grow. It works. OK, great. And finish, maybe a couple more minutes. I finished by just stating another theorem. So, yeah, so this film is maybe slightly disappointing because we don't get explicit bounds. But I say in the generality it's stated, I don't think it's reasonable to expect explicit bounds. But we could try and prove explicit bounds in other cases in projective space. And this is the last theorem. Yeah. So we're going to do, what's the next thesis variety after projective space? Quadratic hypersurface. Pn be a smooth quadratic hypersurface. And we need to assume there's enough variables. This, I mean, we could this of small of conics and quadratic surfaces need to be dealt with separately, but the statement of the theorem should surely hold in these cases. So I need to make sure that n is greater than or equal to 4. So I'm not looking at conics and quadratic surfaces, but yeah, they can be dealt with. Similarly, I'm going to let omega in x of q in. Then if we count the number of rational points inside our thin set, our bounded height, the statement says b to the n minus 1 minus some doubt of n. So I should clarify, b to the n minus 1 is the usual main term. So if you count rational points of bounded height on quadratic hypersurfaces in Pn, you find there's b to the power of n minus 1 of them. So we've got a saving for this. And I'll tell you what our saving is. So, well, you can take any delta of n which satisfies a half minus 7 over 2n plus 4. And I'll note that this delta of n, it tends to a half as n tends to infinity, which agrees with, well, if you're taking the limit, with the same bound from the result of Say and Cohen. Because they managed to save a factor of b to the half, and we can save b to the half in the limit, as it were. Okay, and I'll briefly explain how we prove this theorem. So yeah, we develop a version of the large sieve for quadratic hypersurfaces. So the theorem I wrote at the beginning, yeah, we have an analogous theorem we've proven for counting rational points of bounded quadratic which satisfy conditions modulo each prime. Prove this using the circle method, in particular Heath-Brown's delta symbol version of the circle method, because it's one to use for quadratic hypersurfaces. And then we've got this version of the large sieve. So these methods are really quite general, and we can just plug this general plug these bounds like this lemma 1 and everything into the large sieve, and then we, after balancing, we get some extra terms. So our version of the large sieve is slightly weaker than the one because we've got some extra terms you have to take care of, but it spits out this result. Anyway, that's the end of my talk. Thank you.